I want to talk about the physics of voice. When you're in a conversation with another person and they take more than half a second to respond, something feels off. Not wrong exactly, just slightly broken. Your brain registered a delay that does not belong there. Now imagine you are building a voice agent. Your user asks a question, your system transcribes the audio, runs through a language model, synthesizes a response, and streams the audio back. In a new implementation, each of those steps is sequential. One finishes before the next begins, and you end up with a response time that is closer to 2 seconds or 200 milliseconds. 2 seconds, it's not a conversation, it's a phone tree. In this episode, I am going to show you how to hit a sub 200 millisecond latency budget using the ElevenLabs 11 Flash version 2.5 model and bidirectional WebSockets. We built a FastAPI server that streams speech in, passes it to an LLM, and starts playing audio back before the sentence is even finished. This is episode 1 of the Voice AI Engineering series. Let's get into it. Before I build anything, I want to show exactly why sequential pipelines are a wrong starting point and what the numbers look like. Here is what a new voice pipeline looks like. Step 1. The user speaks. Your system receives audio frames and sends them to a speech-to-text service. Wait for the full transcript. Call the 300 millisecond on a good day. Step 2. You send the transcript to a language model. You wait for the full response. Call that 800 millisecond. Maybe a second. Step 3. You send the full response text to a text-to-speech service. You wait for the audio file, call that 200 milliseconds. Add those up, and you are at 1.3 seconds before the user hears anything, and that is a good day. On a loaded inference server, or with a complex prompt, you are looking at 2 seconds plus. Now construct that with a streaming cascade. The speech-to-text model does not wait for silence before returning results. It streams partial transcripts in real time. As those partials come in, you start building the LLM prompt incrementally. The moment the LLM starts producing tokens, you pipe those tokens into the TTS engine. The TTS engine converts the first sentence to audio and starts playing it back while the LLM is still writing the second sentence. The user hears the first word within 200 milliseconds of request. The difference is not an optimization, it's an architectural decision. Sequential is wrong for voice. Cascade is the only production viable pattern. Let me show the architecture we are building before we write any code. The architecture for this episode has 3 components: a browser client, a FastAPI server, and ElevenLabs WebSocket endpoint. The browser client opens a WebSocket connection to our FastAPI server and starts streaming microphone audio frames. We use the browser's media recorder API to capture audio at 16 kHz. That is the sample rate even 11 Flash v2.5 is optimized for. The FastAPI server is where the logic lives. It receives the audio frames from the browser, passes them to a speech-to-text service for transcription, builds the LLM prompt from the partial transcript, and opens a bidirectional WebSocket connection to ElevenLabs. As the LLM produces tokens, the server pipes them to ElevenLabs. As ElevenLabs produce audio chunks, the server pipes them back to the browser. 2 WebSocket connections in parallel, one facing the browser, one facing the ElevenLabs. The FastAPI server is the bridge. The key insight is that all 3 steps, transcription, inference, and synthesis, are happening concurrently. The server is not waiting for any of them to finish before starting next. It is orchestrating 3 streams simultaneously. The orchestration is what this episode is about. Let me explain ElevenLabs bidirectional WebSocket before we build the cascade. The ElevenLabs bidirectional WebSocket is not a typical streaming API. Most streaming TTS APIs work like this. You send your complete text and you receive audio chunks as they are generated. This is one-directional streaming. You send once, you receive many times. The bidirectional API is different. You send text chunks as they arrive, incrementally as the LLM produces them, and you receive audio chunks in real time as each text chunk is synthesized. This means the TTS engine is working in parallel with the LLM. While the LLM is writing sentence 2, the TTS engine is synthesizing sentence 1. While the TTS engine is synthesizing sentence 2, it's already playing sentence 1 in the browser. There are 2 types of messages you send over this connection. The first text input message, a JSON object with text field containing the current chunk of the tokens of the LLM, and a try trigger generation flag that tells ElevenLabs whether to attempt synthesis immediately or to buffer for more context. The second is a flash message. This is the important one. When you detect a sentence boundary, a period, a question mark, you send a message with flash set to true. This tells ElevenLabs to force synthesis of everything it has buffered so far and return audio immediately, without waiting for more context. This is the mechanism that gives you sentence by sentence audio streaming behavior. On the receive side, the message contained base 64 encoded audio chunks at 22 kHz in PCM format, ready to stream to the browser. Now let us build the streaming cascade, the code that ties STT LLM and TTS together. The core of the system is what I am calling the streaming cascade. It's an async pipeline with 3 stages. Stage 1 is the transcription stream. We use streaming SSD client. In this demo, we use Assembly AI streaming API, but the pattern works with any streaming SSD that emits partial and final transcript events. As audio frames come into from browser, partial transcripts flow out. When the user finishes speaking, a final transcript event fires with the complete utterance. Stage 2 is the LLM stream. We take the final transcript and call Claude, or whichever LLM you prefer, with streaming enabled. As tokens arrive, we push them into the ElevenLabs WebSocket connection in real time. Stage 3, the TTS stream. As we push tokens into ElevenLabs, audio chunks flow back. We detect sentence boundaries into the token stream, a period, a question mark, and send a flash message at each boundary. This forces ElevenLabs to synthesize and return current sentence immediately without buffering. The output of stage 3 is stream of base 64 encoded audio chunks. We forward those to the browser over the client WebSocket. The browser decodes and places them in order. The entire pipeline is non-blocking. Nothing awaits complete response. Everything flows. Let's open our Visual Studio. Sorry about it. VS Code. Let's go to the episode 1 real-time TTS. As the stream section, we have the cascade.py. Look, the stream cascade method is async, and we have an async pipeline code. In production, this stage is SSD, LLM, and TTS. Here we kept this deterministic and stream safe. Now let me explain the chunk length schedule, the single parameter that most affects your latency, quality. That's a trade-off. When the ElevenLabs engine receives that text chunk, it has to decide when to synthesize them. If it synthesizes too early after receiving only 2 or 3 words, the audio sounds choppy and unnatural. The engine does not have enough context to understand, parsing, and apply the right prosody. If it waits too long, accumulating a full paragraph before synthesizing, the audio sounds natural but latency is bad. The user is waiting for the whole paragraph to be generated before they hear anything. Chunk length schedule is the parameter that controls this trade-off. It is a list of integers, the number of characters the engine should accumulate before attempting its first synthesis. It is second synthesis, it is third synthesis, and so on and on. A schedule of 150, 200, 400 means attempt synthesis after the first 150 characters. Then again after 200 additional characters. Then after 400. After that, the final value repeats. For sub 200 millisecond latency target, I use schedule 1 of 120, 1 of 150, 250. The first chunk is short, just enough for a natural sounding sentence fragment. Subsequent chunks are longer because by then the user is already hearing audio, and the perceptual urgency is lower. For cases where naturalness matters more than raw latency, like narration or podcast style audio, I use a schedule of 250, 350, 500. It sounds much better, but the first audio arrives closer to the 300 milliseconds. Pick based on your case. Real-time conversation, go short. Narrative audio, go longer. Also, we can see the default factory lambda values assigned in the chunk scheduler here, like those. And we can calculate the next chunk characters, like this. Even with an aggressive chunk length schedule, you can still get a gap between the end of a sentence and the start of audio playback. The reason is buffer. When the LLM generates the last few tokens of a sentence, the ElevenLabs buffer may not yet have reached the threshold in your chunk length schedule. So the engine holds those tokens, wait for more text before it synthesis. The fix is to send a flash message to the moment. You detect the sentence boundary in the LLM token stream. A flash message tells the ElevenLabs engine, I am done sending text for this sentence. Synthesize whenever is in the buffer right now, don't wait. In the cascade.py code, the The sentence boundary detection is simple. Watch the token stream for a period, question mark or exclamation mark followed by a space or end of stream. When you see one, immediately send a WebSocket message with flash set to true. This gives you the best both worlds. Inside the sentence, chunk length schedule controls pacing for natural prosody. At sentence boundaries, the flash signal overrides buffering to eliminate the tail gap. The combination, an aggressive first chunk schedule and flash at sentence boundaries, is what gets into you the sub 200 millisecond range reliability, not just on average. Let's go back to the cascade.py. Look at the flash, index greater than 1, and chunk ends with punctuations like exclamation mark, question mark. The complexity is in understanding why it matters, not implementing it. It's just an easy like this. Now let me show how to measure whether any of this actually working, because you need real numbers, not gut feeling. There is a temptation to tune voice pipelines by ear. It feels fast, it feels slow, more flash, less buffer. Don't do this. Instrument everything. There are 3 latency measurements that matter for a voice pipeline. First, speech to first token latency. The time from the user stops speaking, the end of the final transcript event. 2, when the first LLM token is received, this is your LLM cold start. If it is consistently above 200 milliseconds, you have an inference problem, not a TTS problem. Second, first token to first audio latency. The time from when the first LLM token is sent to ElevenLabs to when the first audio chunk is received back, this is the time the TTS engine needs to build enough context to synthesize. With an aggressive chunk length schedule, this would be well under 100 milliseconds. Third, end-to-end latency. The time from the end of the user's utterance to when the first audio byte is played in the browser, this is the number that matters to the user. It should be under 200 milliseconds for a natural conversation field. In the server code, we log all 3 Python's time.perf counter. We write the timestamps to a structured log in JSON format. After each demo run, we query the log compute P50, P90, and P99, not just the average. The tail matters. Alright, let's check the cascade.py. Look at the timestamp injections here. In the final transcript, first token received and first audio received. And first token received TS to millisecond is latency of the start. And final transcript to millisecond is rounding to be 2. Now I will run a demo. I have a terminal demo here, demo terminal py, and I will show actual numbers in the terminal. I won't guess the sub 200 milliseconds. I will prove it now. Let me open a terminal from here. Let's go inside the episode 1. Let's run this demo terminal. It will print out in the end the total latency at millisecond and final transcript to first audio millisecond. With the total latency in milliseconds. P50 is 0.03, P90 is 0.04, P99 is 0.04. Very quick. And final transcript to first audio milliseconds is 0.03, 02, 90 is 03, 99 is 03. Also, you can download this from the GitHub and test it yourself. You can go to my GitHub repositories, Voice Agent Architect Lab, and clone the code from here and use the episode 1, the real-time TTS. Let's go back to slides. The FastAPI server is the bridge that holds all 3 streams together. It exposes a single WebSocket endpoint at WS voice and the browser connects here and starts sending audio frames as binary WebSocket messages. Inside the handler, we open 3 concurrent tasks. The first task is reads audio frames from the browser connection and feeds them into the transcription stream. The second task is reading the partial transcripts and feeds them to LLM stream, accumulating the tokens and detecting the sentence boundaries. The third task reads LLM tokens, pipes them to ElevenLabs, and forwards the audio chunks back to the browser. All 3 tasks run concurrently using async error gather. None of them block the others. If the transcription stream is slow, maybe the user has long pause, the LLM and TTS streams simply wait their input. The async nature of the pipeline means there is no busy waiting. There is one error case worth handling explicitly. If the ElevenLabs WebSocket closes unexpectedly due to rate limiting, maybe network interruption, or quota exhaustion, we catch the disconnect event, log it, send a brief error message to the browser client and close the browser connection cleanly. Do not let downstream failure silently hang the browser session. The full server is about 140 lines of Python. Not large. The complexity is in the streaming coordination, not in the server scaffolding. Let's go to the server PY. Here's the WebSocket endpoint with a decorator. As you can see, it waits to accept, and asynchronously it logs events here, and it awaits the send action like here. Read audio, transcribe, and infer, synthesize, and stream. That's it. In the README, we have a bash command that runs this with UE. Let's do it. Oh, we need to first create the virtual environment. Let's do it. Let's activate the virtual environment. We are in the virtual environment. Let's install the requirements. We need to upgrade the pip. Now we try back to requirements again. Let's increase the Python version. Let's decrease the version number of the numpy like this. Let's try the requirements now. Instead of changing the numpy version in the requirements, we can use the Python 3.13. Let's activate that. Now install the requirements. It should be done now. Now the lang chain is installing. LangGraph also too. There's no problem now. Everything is installed. Let's upgrade the pip now. One final time. It's upgraded. Right now we can, with Unicorn, start the episode 1 real-time TTS server on port 8011. Okay, let's go inside the folder because import path issues are emerging. Let's go inside episode 1 real-time TTS. Let's start the Unicorn server from there, port 8011. Yes, now it's running HTTP localhost 8011. Let's start another terminal. Let's go inside also from this terminal to in episode 1. And as you can see, we have a demo latency WebSocket testing demo here. It prompts, hello, this is a latency test. Please summarize the last quarter of blah blah in one sentence. Give me a 10-word closing line. Let's see what happens when we run this. Run the demo latency py. Oops. WebSockets is missing. Let's install the WebSockets because it's missing from the requirements. I think I need to add them to requirements too. Now we have the WebSocket and run the demo latency now. Very good. The total latency is P50 is 20.24, P90 is 0.32, 99 is 0.32. Final transcript to first audio is P50 is 0.03, 90 is 0.04, and 99 is 0.04. Very good numbers. Let me close with the key patterns to take away from this episode. 4 things take away from this episode. 1. Sequential is wrong for voice. The cascade architecture, SST, STT, LLM, and TTS running concurrently, each feeding the next data arrives, is the only pattern that gets you under 200 milliseconds reliably. 2. Chunk length schedule controls prosody versus latency. Start short, 120 characters. For the first chunk, that's okay. Let subsequent chunks grow. Tune by measuring, not by ear. 3. Flash at sentence boundaries. Without it, the final tokens of each sentence sits in the ElevenLabs buffer waiting for more context. Single flash message eliminates that tail gap. 4. Instrument 3 timestamps. Switch to first token to first audio, end to end. Know your P90, not just your average. It felt fast in the demo. It is not a production quality signal. Okay. The full code is in the Voice Agent Architect Lab repository, in my GitHub repositories. You can check from the GitHub Voice Agent Architect Lab here. In episode 2, we move this web demo to the PSTN. Real phone calls using Twilio media streams and conversation relay. We will handle 8 kHz mu-low audio encoding, acoustic echo cancellation, and architectural decision of when to use managed relays versus build the proxy yourself. If you like this video, please subscribe and hit the like button, and see you there.